All right, folks, we are on the bottom of page 13, and we're going to talk about this FRQ. This is all in the calculator. Okay, so we need to talk about what some of this stuff means. So first of all, it says 4 times 0 to 31, the rate of change of the number of mosquitoes on a tropical island at time t days is modeled by the following function in mosquitoes, mosquitoes per day. Okay, and there are 1,000 mosquitoes on this island at time 0. So we're given a lot of information here. Okay, and we need to make sure that we interpret this correctly. First of all, we do have our time interval, and this is going to help us if we're graphing and if we have to change the window. Here, the rate of change. What does that mean? Okay, slope. That means the derivative, right? Well, in this case, it says the rate of change is modeled by. So what can you say about this function? It's not the slope. It's a derivative. And the other clue that this is a derivative is the per. Okay? So you need to make sure that you understand what you're given. So this is actually a derivative. This is not the original function. So if this is the rate of change, or basically how the number of mosquitoes is changing per day, how would I get the number of mosquitoes if I was asked for it? Yes, sir?
You take the integral?
Yes, we would integrate. Okay, so reading what you're given is extremely important first before you even jump in. In part A, it says show that the number of mosquitoes is increasing at time t equals 6. If you're given the derivative, how do you know that the number of mosquitoes is increasing? What do we look at?
Where it's 0 equal to 0,
Where it's what?
where velocity is equal to 0, and then put it on the number line to where it's increasing.
How do you determine if velocity is increasing or decreasing?
Positive.
So we're looking to see if at time 6, the derivative, which you indicated velocity, but this isn't velocity. Yeah, it's okay. Nope, it's fine. This is a derivative, is positive. So what we want to do in part A is go into the calculator first. Okay, and we want to go into y equals, and if you have anything in there, make sure you clear it out. Let's put our function in first. Okay, and then at time 6, we want to see what's happening. So what they're saying is show that the number of mosquitoes is increasing. So you told me that I'm looking to see where velocity, which you're saying is the derivative, is positive. Okay, so if I go into the table, I have a list of everything here. Is that proof enough? We're looking for where the derivative is positive. So what we would write is r of 6 is equal to 4.438, which is greater than 0. So the number of mosquitoes at time t equals 6 is increasing. Okay, questions on how we determine this, what we're looking at, just to be clear. Okay, so let's look at B. It says at time t equals 6, is the number of mosquitoes increasing at an increasing rate or increasing at a decreasing rate? Okay, so what are they asking? Say again?
Acceleration.
Okay, so if we know that this is a first derivative, they're asking about what is happening with the second derivative. So what we're looking at, if we're looking for the rate, we want the rate of r of t, excuse me, which is really r prime of, and they said at time 6. So if you still have this in your calculator, if you go back into y equals, we set this up at the beginning of the year where you have your derivatives at the bottom somewhere. So this is saying take the derivative of whatever I put in y sub 1. So I'm going to highlight this, and I'm going to go into the table. What am I looking for at time 6 in the table?
Where
I'm going to go to times 6, but what am I looking for?
Where velocity and acceleration at the same time. So the first and second derivative.
You're so close. Not like I'm not asking if it's speeding up or slowing down. I'm asking are the number of mosquitoes in
6. Equals 6.
Okay, I'm going to go in there and you just tell me. So here's times 6. Is the number of mosquitoes increasing at an increasing rate or a decreasing rate?
Decreasing.
How are you determining that?
Different signs between the first and second. Like,
I know you know, but the way you're explaining it is not correct. It has nothing to do with you're not comparing the signs. You know that the number of mosquitoes is increasing, true? Because this is positive.
yeah.
At a decreasing rate, just because acceleration is negative. You're not comparing the signs. Because that would be speeding up or slowing down. Okay, So, in this case, we would say r prime of 6 is equal to, is this negative 1.913? Therefore, I don't know, I'm just picking some words. The number of mosquitoes is increasing at a decreasing rate. Okay? We know this is increasing because we looked at the rate at which the number of mosquitoes, or what was happening to the number of mosquitoes at time 6. The value was positive, so the fact that they're increasing at time 6. However, the rate, which is the derivative of what we were given, is negative, therefore decreasing. So graphically what this means is, first derivative, the graph is above the x-axis, concave down. True? Because this is negative. Okay, part C. According to the model, how many mosquitoes will be on the island at time t equals 31? Well, I kind of asked that question, and Max answered, if I had to determine the number of mosquitoes at time 31, I do need to integrate, but I have to consider something else. What do I have to consider?
Initial.
Yeah, how many we started with? There are 1,000 mosquitoes on the island. So at, let's see, r of 0, okay, plus the integral from 0 to 31 of r of t dt. Do I have to rewrite that function? It's already defined in the problem, so I'm good to go. So we know that this is 1,000. So if I go into my home screen and I have my function in the calculator already, I'm going to type in 1,000 here, plus you go in and grab your definite integral, which is option 4. We're going from 0 to 31, and our function is where? Yeah, it's in y sub 1. So I'm going to go into alpha trace, grab y sub 1 with respect to x. Now this is very specific. It says round to the nearest mosquito. Those of you with newer calculators probably already have your answer. Huh. Why is it 964? Based on what we answered in our last question, what's happening? Okay, so something's happening. They were increasing. There is a point somewhere after time 6 maybe, or anywhere between time 0 and 31 where, I don't know, somebody came in with pesticide, or maybe they just started dying off. I mean, mosquitoes don't live forever, right? Okay. Yeah. So how many mosquitoes? 965, 964? 964. Okay, you need to speak up.
Sorry, could you explain again why we took the integral?
Why did we take the integral?
To find the mosquito.
Because in the original statement it said this is the rate at which the mosquitoes were. Yeah, it's mosquitoes per day. So it's the rate at which they're procreating or appearing on the island. Okay, so if you have a rate, in order to get the number of mosquitoes, you got to go backwards.
Okay.
Okay, that's why it's important. You got to read and highlight what you can, underline it, whatever it is. Okay, and then I asked that question, and Max said we had to go backwards. Okay, part D. So, to the nearest whole number, what is the maximum number of mosquitoes for times 0 to 31, and show the analysis that leads to your conclusion. So this is where some people get confused, because if it says show the analysis, an example would be in the writing prompt, people just start writing words, 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 words. And what do you start doing? You're just twisting yourself into this not making any sense. Sometimes your analysis is just the math. So don't we know that at time 0, we have 1,000 mosquitoes? That was given, true? And then we also figured out that at time 31, we had how many? 964 mosquitoes. What I need to look at is there a possibility that I could have a higher value somewhere? Because we determined that somewhere between time 0 and 31, there's got to be a peak somewhere. Because we calculated the number of mosquitoes was increasing at time 6, but then at a decreasing rate. So something has to be happening there. So we need to look at the graph of the derivative. So if we're looking at the graph of the derivative, we need to see, based on the graph, if there is a relative max. How do I determine that based on the graph? You got to think back, because we've done this with the derivative. Yes, sir?
Where the derivative equals 0.
Okay, so we're looking at where the derivative is equal to 0, but now how do I determine if it's a max there? Something has to happen. I see some people are going like this, so I'm assuming that you're thinking maybe number line.
Critical number.
Okay, critical. So that 0 is going to be a critical number, but something has to happen. Yes, I'm changing from positive because that's where the original function would be increasing to negative. So I'm looking to see where the derivatives graph goes from above to below. Okay, so let's go in. I'm going to need to change my window. X has to go from 0 to at least 31, so can I make it 40 just to be safe? And I had graphed something else. My min, I don't know, 10. Let's go to negative 10. Negative 10 to 10. I don't know if this is right. What if it's wrong?
Then we go back and change it.
Sure. Okay. Okay. Awesome. All right. So this is whoa. Well, stop. Obviously, what is this graphing? What did I forget to unhighlight? Yeah, my derivative. Okay. Yep. Okay, and I'm going to go back actually into the window, and I'm going to change this to 31. And the reason why is I don't want to confuse myself. I'm going exactly out to 31. When I went out to 40, I saw too much of the graph. Did you guys understand what I just said? Which is, I made my window from 0 to 40, but it was too much. Because I could see something else over here. I really only care about time 0 to 31 because that's what's given to me in the problem. Okay, so we were told that we want to see where the graph is going from above to below. Do we see it? Now you have to know this because look, I have 2 critical values here. Okay, so in order to calculate this, you could calculate the 0, which means you have to give it a left bound, a right bound, and a guess. Or you can go back in here, excuse me, and just put 0 into y sub 2. Where does y equal 0? Where does y equal 0? Yeah, it's just the x-axis. So when I graph this, I'm not even going to see it, am I? But how does this help me? This is the one where all you have to do is go enter, enter, enter. It's just quick. So I want to go in and calculate the point of intersection. So I want option 5. First of all, I need to find my cursor. So it's down here somewhere. So I'm going to go to the left because I want to get closer to this. Here it comes. There it is. Is this the first curve? Meaning, is this the first graph? I press enter to say yes. Is this the second one? Yes. And then I'm guessing, I'm just going to press enter because it's closest to that one. So this is the time at which there is a relative max. If this is the time, does it tell me what that value is? So how do I get it? Plug it in. What does that mean? Plug it in. There's a plug right here. Do I plug it in right there?
I don't think I have a fit.
Okay. So then what do I do? What?
Plug it somewhere.
Oh my. You better go easy there, buddy. Okay, I need to plug that value in somewhere. How do I figure out the number of mosquitoes at time 7.8539? Yes, the integral. Okay, so at time equals 7.8539, I need to know how many mosquitoes. Someone tell me the setup, please.
R0.
Yes, 1,000, R of 0 plus the integral up from 0, yep, to 7.8539 of R of t dt, which is in y sub 1. Excuse me. So, I am lazy, yes, not always, but it's already in there. So if I hit second enter, all I need to do is go up and change this upper bound. 7.8539, is that right? 8539. Okay, enter. Wow. Okay, how many mosquitoes? Yeah. So we have 1,039 mosquitoes. So this right here is the maximum. This is my analysis right here. You don't have to say anything else. That's your analysis.